We're going to start off this morning with a round of lightning talks. And you know, I've organized things into blocks. This first block is largely time series oriented. If you're a traditional time series economist, or even if you're not, I think there's some interesting stuff in here. So we'll start off with 5 lightning talks. We've got Stephen Bronder, who's going to talk first, and he's going to look at sort of some forecasting and machine learning in a certain framework. So Stephen, if we can have you come up here and we'll get things started. So there you go, Stephen.
Thank you.
Thanks.
Hi everyone, good morning. Today we're going to be talking about something simple so everyone can relax, keep eating. This is going to be a nice and simple walkthrough of something I've been doing about a project for a year now. This quote from Hadley Wickham is extremely important to me. The idea of building things that allow for people to safely do statistics. Here we're going to be talking about a safe framework for forecasting that I think really needs to exist. Currently there's this great divide between forecasting and machine learning that I see. I see some people trying to poke around, get the edge of where between we could be going. But when I look at this project, I say, why don't we have both? Why don't we do some nice cafeteria statistics? We'll go into machine learning, we'll take what we want. Go into forecasting, we'll take what we want. And I'm going to do an example to show how we're doing this process. So just for some example data, we have the weekly percent change in Apple's closing price. I just grabbed this from Quandl. It starts, the training data we're going to use is from 1980 to 2017, and the holdout data is from just 15 days we're going to be forecasting into the future. It's from just March 30th to April 20th. So in the MLR framework, you can see here I just do a little bit of stuff to take because Quandl gives back an XTS frame, you have to turn it into a data frame. We first start with the task that holds all of the data and metadata for our particular task that we're going to be doing. In particular, we have a make forecast regression task. We give it an ID to tell us in the future what we want, what this was. We give it the data. We tell it our target is close, the closing price. We tell it the date column so it knows what column is the dates. And here we tell it this has a frequency or seasonality of 5. There's not really a seasonality of 5. I just kind of chose it to show that we could do it. This printout gives you a much better idea when you go and look later and see we're doing weekly percent change in Apple closing price. It tells you the start and end dates, the frequency. Notice we have no features here because we're doing a univariate task. But yeah, we also can confirm that we have no missing data and that sort of thing. So here, this is fcregression.garch from this make learner function. It comes from the rugarch package. All of these arguments originate from arguments from spec and fit in the rugarch package. So we just construct this forecast learner, and we put that through train, given our original task with our data, and we have a trained Garch model. We then use the predict function, giving it the test data, and it'll give back an object that just holds both of those things for us. And we can do a performance evaluation given that prediction object. And here we can look at multiple measures. Here we look at both MACE and RMSE. We feed it the task and the model. It tells us we get a MACE of 0.17. It's probably because the MACE here is a seasonal MACE we're using. So seasonal MACE of 5 is probably not terribly good. But here's a nice little graphic to kind of show, hey, like we can do forecasting and it looks kind of okay. But really machine learning, we want to be able to tune hyperparameters. That's what we really care about. And just if those are kind of small, you can see the blue line is the truth, the green line is the response, and the higher and lower wiggly ones are the upper and lower quantiles. Because we were able to do quantile. We were able to do the upper and lower bounds for our forecast. So we're going to talk now about tuning the hyperparameters of a Garch model. So we make this param set function, and we pass in a bunch of other sub-functions that define the parameter space of how that we'll be tuning over. You can see here, for instance, like we have sgarch, csgarch, and fgarch. You can see that for submodel, we say, hey, submodel is only used whenever fgarch is on. Whenever the ID for model is set to fgarch, we also want this submodel hyperparameter, but in no other times we want that. So this essentially just constructs that hyperparameter thing that we're going to be working over. Control here is what we're going to be using to search over that hyperparameter space. This one's called iterated f-racing. It's just a machine learning technique for searching over hyperparameter spaces for their objective function, the space that minimizes the objective function. And we're going to do 21 growing window cross validations. You can see the bottom part of this graphic shows, this is from Carrot originally. You can see that essentially we are going to be forecasting with a horizon of 15. We have an initial window of half the data, and just for purposes of time, we skip forward 220 steps every iteration of our resampling schema. And so that bottom graphic shows you that we just kind of slide forward the window at every iteration. So now it's pretty simple. We build a base model for Garch.mod. Parallelization is incredibly simple. Here we're using 7 cores from the we're going to use Parallel Map Library, completely integrates in MLR. And we do tune params, which is the heart and soul of this model, which is the heart and soul of MLR, essentially. So we pass it the Garch model, the task, our resampling schema, our parameter set we're tuning over, our control structure, and what measure we're going to be using to evaluate our models. And we get back a result, and it gets kind of fallen off the page, but that's not that big of a deal. In R, it would be normally, you would see all of it. But we can take this final tuned model that we did, to train the final model, we use set hyperparse. We pass it the optimal tune parameters from Garch.res. CacheX is where we store them. We train the model again, we do predictions, and we do performance measures again. You can see that we do about 50% better in this toy example. And here's a plot of that. Once again, green is the response, the predictions, and the blue is the truth. And we have the upper and lower quartiles. And to kind of just show you the difference, on the left side, we have the tuned model, and on the right side, we have the untuned model, to kind of show like the difference between having a tuned model and not. And so that's it. We have a nice, this is an interpretation of how you could use machine learning and forecasting together. I think that, I think it works pretty nicely. I think it's a little good cafeteria stuff. I still have time to talk. That's surprising. So yeah, you can check out the forecasting branch online, and thank you very much. Oh, I also wanted to say we could also forecast with all the machine learning models inside of MLR. So thank you. Thank you.
Next up, we'll have Leopoldo Catania, who is going to talk to you about something you may have heard if you were here a few years ago. He's going to talk to you about some score models. So.
Okay, hi to everyone. So today I'm going to talk about generalized autoregressive score models in R. So we built this gas package together with David and Chris, and this is a project that comes from Google Summer project of last year. So let's make an experiment. Suppose you are employed in the risk management unit of a financial institution, and so what you are required for? You are required to build internal models, predict future value at risk levels, and respect capital requirements. So most likely you are going to do an historical simulation analysis that unfortunately does not work, or an exponential weighting moving average scheme that unfortunately is not working either. So maybe if you are a bit sophisticated, you are going to employ Garch or stochastic volatility. Unfortunately, we also saw from the previous presentation that Garch does not work well for quantile prediction. So what about gas models? So gas models are new models that have been proposed recently in 2013. An important point is that gas models with a Gaussian conditional distribution are equivalent to a Garch model with a Gaussian conditional distribution. So when you see gas n in this presentation, it means that this is Garch, okay? So here I report a picture taken from a paper that I have with David and Chris, and we can see these are one step ahead forecast of the 1% value at risk for General Electrics. So you can see at the end of the sample how a spike affects the quantile prediction. So this is very bad if you are in risk management, because due to the persistence of the volatility, you have that it takes a lot of time to go back to the unconditional level, and you pay money for that because you cannot invest. You have to respect capital requirement. This is quite common. This is Apple. This is the same series as the previous presentation. That's a profit warning. These are absolute returns, and I'm comparing gas with Garch, and you see how bad Garch behave for filtering volatility. So this is very bad. You don't want that. This is very common in finance. We all know. So this is North Pole returns, absolute returns, and you can see that this happens very frequently. So you always have outliers in financial time series, and you always get misleading forecasts when you employ Garch. This is due to the fact that you use past square returns to update the volatility, and this is okay just if returns are Gaussian, and this is not the case for financial returns. So let's look at the plain GARCH-1 model. So if you are the sophisticated one of your colleagues, you are maybe going to employ this one. For stochastic volatility, it is exactly the same. So the filter behaves quite similarly. So you can write GARCH-1 in this way, so it seems like more an autoregressive process, where UT is a martingale difference. Okay, under the generalized autoregressive score framework, you will substitute that martingale difference with another martingale difference, which is the one reported at the end of this slide. So this martingale difference is bounded by the degrees of freedom of the student t-distribution. This in the robust literature, this is called Winsorizing. So you have that the new sympath curve is bounded by the degrees of freedom. So if you got an outlier, your filter would not increase the volatility in a crazy way like GARCH would do. So GARCH in this picture is the quadratic function. You see that it obviously goes to infinity. Now with GAS, instead, when you employ a student t-conditional distribution, you get a bounded update. And so this is why you get this not so explosive update of the volatility parameter when you got an outlier. This is something that you want if you work in risk management. So generalized autoregressive score models are much more than just for financial application. So you can have a parametrical assumption for your vector of observation. This can be either univariate or multivariate. And you can have a set of time-varying parameters, which is theta in this slide, and psi, vector of constant parameter. Then you build an updating equation for your vector, for your reparametrized vector of time-varying parameter, which is theta tilde. And you just use a quantity, ut, which is proportional to the score of the conditional distribution. So you just take the derivative of the log of the density you assume for the data, and you use this as an information to update your set of latent time-varying parameters. This is a new, natural way to update parameters, and it's not like GARCH, okay, that say, let's put square returns. Why? Let's put absolute returns. Why? GAS just say, you have to use this because your distribution tells you where to go in order to have an higher probability mass. So we built this GAS package for R. You can find 2 papers that describe the main functionalities. So you can employ GAS models with univariate and multivariate time series. It is mostly written in C++. There is some RCPP and RCPP armadillo stuff going there. So it works in parallel. It is part of a Google Summer of Code, and it is available on CRAN and GitHub. So as I said, there is much more than financial econometrics in GAS. So you can employ a lot of different distribution for your data. So you can have count data, you can have positive data, you can have whatever kind of data, and so you can build a GAS model for the data you have. So thanks, everyone.
So when I was a grad student at the U of C, I was bedeviled regularly at presentations by Arnold Zellner, who would always butt in asking, but what about the Bayesian perspective? So it is very appropriate that coming from the University of Chicago, we have Guanhao Fang, who's actually going to talk to us about a Bayesian perspective on time series. So thank you.
Hello, everyone. So I'm a PhD student from University of Chicago. And this paper, so the title is very informative, regularizing Bayesian predictive regressions. The paper is originally for the Bayesian community, but if you are not one of them, then I can show you that their stuff is quite related to any other stuff in statistics. So what do we do in this paper? Basically, on one side, all Bayesian studies, they require some prior information, which can be motivated by anything, economic theory, or any kind of constraints. However, for statistical regularization methods, we usually use like adjusted R-square, AIC, BIC for model selection, especially for those high-dimensional model selection, to get a parsimonious model to maximize the out-of-sample prediction power. And then in this paper, we developed a duality to connect these two frameworks. Okay, so we say that, okay, many Bayesian studies, they're related to the regularization methods. And then we can use the regularization methods to provide prior sensitivity analysis for all Bayesian studies there. Because we also know that many Bayesian forecasts, they are quite sensitive to what prior they really use. And then right now we have a lot of fast computing package in RDAT to provide convex optimization for regularizations. So we can use these new tools to evaluate all Bayesian studies. So the motivation example is the basic VAR1 model. As you can see, the capital letter B, which is the AR coefficient, and the sigma is the noise covariance matrix. For all regularization methods, we need to specify two things. The first thing is the likelihood, or the least squares. And the second thing is a penalty function. If for AIC, BIC, just count how many parameters you really use in B and sigma. And then, like, the objective for regularization methods there is like minimize the penalized least squares or the penalized negative log likelihood. However, here I introduce you a map estimator from the Bayesian side. So a Bayesian guy, they will view that the function LB sigma here, they are just the log likelihood. Yes, okay, that's for the model. And the phi B sigma for the penalty there, which is the prior distribution in the Bayesian side. And if we view the L function and the phi function as a hierarchical Bayesian model, then we can see that, okay, to minimize the penalized least squares or minimize the penalized negative log likelihood, which is the same to maximize the posterior density. So the map estimator here, which is the maximum of the posterior. Okay, so for any other kind of Bayesian studies, when we study the posterior distribution, if we want to focus on the map estimator, then this is the same as a regularization problem. We can just use all those regularization packages developed to study Bayesian problems. And given this kind of tool, then we can perform a prior sensitivity analysis. Like here, the prior function phi, if we decompose them as two parts, one for the AR coefficient, one for the variance covariance matrix there, we can easily use those little R package like ElastiLab or those sparse matrix package to study the sparse structure for the noise covariance matrix. So the idea is just very simple that any Bayesian studies, they require to know the prior distribution. If we use the normal as a prior, you have to provide what is the mean, what is the variance. And the mean and variance there, they are just like the hyperparameters in a prior distribution. And if we interpret them as a penalty function, these hyperparameters are just like the tuning parameters in the penalty function there. So in any regularization study, when we use the tuning parameter to try to maximize the out-of-sample prediction performance, it is the same. We can provide that prior for the Bayesian studies. This is a quick check for all Bayesian studies there, how you specify your prior distribution. So here is a quick takeaway from our method here. We can use any kind of data-driven methods to specify the prior, and then for regularization methods, we can easily use the regularization path to see how sensitive the predictive value corresponding to the prior specification. And I would like to talk about estimation procedures here if you're interested, so you can download the paper from the website. But we use a market timing strategy to show how effective our method is. Okay, so to perform a Bayesian predictive forecast for S&P 500 assets return, so we show, okay, first of all, in this plot, in the 1-1 plot here, which is the y-hat for the last quarter in 2015, and then you can see that the predicted value changed a lot given the tuning parameter or the hyperparameter in the prior distribution. So sensitivity analysis is something we need to check the studies. If we use that to form a market timing strategy for two asset portfolio, one is the S&P 500 and the other one is the risk-free rate. Okay, then the first column, the left column, which is just using one predictor, the dividend yield. The Y column, we use all predictors together. And the benchmark strategies, one is the historical average, which is the most regularized one in our model, and also the regular way model, which is the least regularized one. And we also compare with the buy and hold strategy. So by the end, you can see that for the bottom two blocks, okay, our optimized strategy and the average strategy, they perform the best in the sample here. Thank you.
Next, we have Jonas Renda, who's going to talk to you about what he might call teilweise co-integrierte, but you might know as partially co-integrated time series. So, thank you, Jonas.
All right, good morning, everybody. I will talk about partial CI. It's an R package for the analysis of partially co-integrated time series. Okay, so we do it like this. During my talk, I would address the following questions. What is partial co-integration? How does it work? How to use partial co-integration? And where is it helpful? So starting with the first question, what is partial co-integration? And to answer this question, it is necessary to understand the concept of classic co-integration, because partial co-integration is a weakening of classic co-integration. So loosely speaking, a collection of time series is co-integrated if they share a long-run equilibrium. And to gain a better understanding of partial co-integration, I will continue with a comparison between classic co-integration and partial co-integration. So imagine a classic co-integration scenario. The residual series solely consists of a stationary mean reverting component, whereas in a partial co-integration framework, we model the residual series as a sum of a permanent component and a stationary mean reverting component. And in the literature, the latter is known as a partially autoregressive process, which is introduced to the scientific community by Butterpa and Summers in 1988. And very recently, my co-author, Matthew Clegg, further elaborates on the model. So next, talking about shocks. Classic co-integration always requires that all shocks to the residual series are solely transient. In a partial co-integration framework, we are much more flexible here, and we allow for transient shocks and permanent shocks as well. So to visualize the difference between the two concepts, I prepare two residual plots for you. And first, the residual plot belonging to classic co-integration, and here we see the typical stationary behavior associated with classic co-integration, right? Whereas if we switch to the right-hand side, we see the residual plot belonging to partial co-integration, and here you see that globally it looks like a random walk, but locally it's mean reverting. And this is typical for partial co-integration, so a combination of mean reverting and permanent patterns. So key takeaway from this slide is that partial co-integration enhances classic co-integration by accounting for permanent effects in the residual series. Oh, sorry. So now that we know what partial co-integration is, we will discuss how it works. So the target time series Y and the factor time series x1 to xj are connected by a partially autoregressive process. That means by a stationary AR1 process and a random walk process. And what we assume is that the innovations belonging to the permanent component, to the AR1 process and to the random walk process are mutually independent and normally distributed white noise processes with zero mean and variances sigma square m and sigma square r respectively. So in our simplest case, we have four model parameters. The parameters are the mean reversion coefficient rho, the variances belonging to the innovations of the mean reverting component and the permanent component, and the co-integrating coefficient beta. But unfortunately, as always, neither the residual series nor the permanent component or the mean reverting component are observable, and therefore the model is transferred into a state space model, and estimation is then performed using a Kalman filter. A key metric of our model is the proportion of variance attributable to mean reversion, PVMR. The PVMR is between 0 and 1 and measures if a particular time series is closer to a random walk or a mean reverting component. The next question I would like to address is how to use partial co-integration, and here we'll outline the four key functions of our package. So fit PCI fits a partial co-integration model to a given collection of time series. Test PCI tests the goodness of fit of a partial co-integration model. State history PCI estimates and extracts the hidden states. And last but not least, Hedge PCI finds K factors from a predefined set of factors which yields the best fit to the target time series. And the last question I would like to address during my talk today is, where is it helpful? And in our little pair trading example case, we would like to model the spread between Royal Dutch Shell A and Royal Dutch Shell B using daily prices. And if we first have a look at the spread time series, we see that, of the plot of the spread time series, we see that globally it looks like a random walk, but locally it's mean reverting. And to clarify what I just said, we use our state history function to disentangle the transient component and the random walk component. So starting with the transient component, it can be seen that the spread time series exhibits a strong mean reverting behavior. And the blue lines you see on the plot are equal to 2 times the historical standard deviation. So clearly a pairs trading strategy could exploit those mean reverting patterns. And on the right-hand side, you see the dynamics associated with the random walk component. And if you would add up the plot of the transient component and the random walk component, this would directly lead you to the plot on the left, to the plot of the plot of the spread. So clearly, RDSA and RDSB are not co-integrated in a classical way, but applying a partial co-integration model seems to be appropriate. And that's what we have done in the next slide. So on the left-hand side, you see the R output of the PCI function. You see corresponding parameter estimates and standard errors. And on the last slide, I said that the spread time series exhibit a strong mean reverting behavior, and this is here quantified by a PVMR of 0.54. And on the right-hand side, you see the R output of the test PCI function, and the random walk null hypothesis as well as the AR1 null hypothesis are both rejected at the 5% significance level, indicating that RDSA and RDSB are indeed partially co-integrated in the considered time framework. If you like what I just talked about, I highly recommend to read our full paper. Check out the corresponding R package. It's available on CRAN under the name Partial CI. Have a look at the initial showcase. And if you're already super excited about it, grab your phones and scan the QR codes and you can immediately download the things. So thank you very much for your attention and enjoy the rest of the conference.
So last for our lightning talks, we will have Carson Sievert, who will come up and actually talk to you a little bit about how we visualize multiple time series. So.
All right. Good morning, and thank you for having me. I'm Carson, and I maintain Plotly's R package. So I'm going to show you a little bit of what we can do for visualizing multiple time series. And if you're not familiar with Plotly's R package, it's an interface to Plotly.js, which is completely free and open source, so the R package itself is completely free and open source. And it's designed to work well with existing R tools. So here's just a mini example of using the QuantMod package to get some financial data and feed that into Plotly. You can give Plotly basically any date object in R, and it'll sort of know how to send that to Plotly.js, or you can give it a vector of strings that are formatted as dates, and it'll know what to do with that as well. And what you get is a nice web-based interactive plot where I can hover over certain values on the plot and see exact values from that time series. And then you can also click and drag to zoom and pan on the x-axis, for instance. And it's very easy to create subplots using the subplot function. And that makes something that's a little bit fiddly if you're working directly with Plotly.js. This is sort of hard to do, but the subplot function makes it pretty easy to just lay out multiple plots in a grid-like structure. So here, I'm just creating 2 different plots. You could scale them to different heights if you wanted to, but here I'm just giving them equal heights. And then notice by saying share x equal to true, then when I zoom and pan on an x-axis, they both share that zoom event. And then if you want, you can reset the axes. It's also easy to say add a range slider to this plot using the range slider function. Then you get this sort of mini subplot at the bottom here, where now if I zoom and pan on a particular region of the x-axis, then you can see not only just the local activity, you can also see the global activity at the very bottom. And then you can also mess with this window if you want to shift the window at all. And I probably should have included some examples where you can include some buttons if you want to, say, shift by 6 months, shift by a year. We have some examples out there like that. And I think we're probably one of the leaders in plotting lots of time series points, and it's very easy to take advantage of WebGL for this. I don't know exactly if we are the leader in this, but I have myself plotted, say, like 250,000 of points in a time series, and WebGL can handle that fairly easily. And you also get the same experience with the zooming and panning. We also have pretty nice support for other financial chart types like candlesticks. So if I just specify an open, close, high and low, and the type of chart as candlestick, then I get this candlestick chart where you can zoom in and hover on specific days to get the actual open, close, high, low values. And something we also do in Plotly is we convert ggplot2 graphics. So here I'm using ggplot2 to create a faceted plot, or sometimes called small multiples, and you get the same plot as you would get from ggplot2, but now it's interactive and web-based. And some nice things that we can take advantage of with this new capability is take advantage of some animation and some interactive capabilities in Plotly. So just by adding this new layer where I'm specifying a frame aesthetic, instead of plotting a line for every year, I can animate over specific years, so I can sort of see how the annual pattern changes from year to year. Another thing I can do is, I've been working on this quite a lot, but we can also do linked brushing in small multiples. So instead of just animating through the years, I could say click and select on a specific year, or query a year indirectly, or paint that a different color. So lots of capabilities there. And you can also embed this sort of framework within a larger Shiny app, which is what I'm doing here. And you can also share these types of linked plots with, say, Leaflet. So that's all I have. Thanks you for having me.